On time. All right. Next speaker is Kevin Strauss. Kevin is a pediatrician and translational physician scientist with 25 years of experience caring for children with rare genetic disorders, integrating community-anchored clinical care with advanced translational science. Across more than 100 peer-reviewed publications, he helped define the mechanisms, clinical course, and treatment of numerous inherited metabolic and neuromuscular conditions, many arising from founder variants in Old Order Amish and Mennonite communities. In 2025, he founded Plowshare Therapies, a gene therapy company powered by the community it serves. PowerShare unites Plain community investors, academic partners, and experienced drug developers to create sustainable, affordable treatments for underserved populations, ensuring that families who participate in research share in its benefits. Welcome to Kevin.
Thank you, everybody. I'm really excited to be here. Thanks to the Family Support Group for inviting me back. I've been to several of these over the years, and it's one of the highlights of my year. I have a little bit of a challenging task this morning. I was asked to give a broad overview of the history of therapeutics and MSUD. And it's a deep and complicated history, but I think it's absolutely fascinating. And for some of the younger families, you may not have had an opportunity to really learn about the origins of MSUD within the history of medical science. So I'm going to take you on a little journey this morning, and hopefully this will set a foundation for some of the more advanced topics you're going to hear about today. So I first want to put MSUD in a historical context. MSUD is an inborn error of metabolism. But what you may not really understand is that the inborn errors of metabolism are a relatively new concept in medical science. And the foundations for that whole class of diseases really started with work of Gregor Mendel, the pea plant experiments. So Mendel really established the principles of heredity in pea plants. And a fan of Mendel was a man by the name of Archibald Garrod. He was a physician in London who was studying patients that developed bone deposits and black pigmentary deposits in their eyes. He eventually named it ochronosis, and this was the very first inborn error of metabolism. Archibald Garrod connected Gregor Mendel's ideas to human chemical traits and found that chemical traits could be inherited and could be the cause of disease. Osborne Folling was a Norwegian high-altitude physiologist and chemist who established for the first time that abnormal brain development could result from these chemical traits. And he did that by diagnosing the first case of PKU, phenylketonuria, using the ferric chloride test, which most people don't know about anymore. But this was a foundational discovery in inborn errors of metabolism. It would be about another 20 years before Horst Bickel and his colleagues discovered a way to treat PKU using a special restricted diet, a diet restricted in phenylalanine. This is one of the earliest diagnosed patients next to a sister who had gotten the treatment. And obviously you can see the difference this made. This was a sensation when it happened in medicine. They recognized that about 5% of the entire institutionalized population in the world had PKU that was undiagnosed. That discovery and the power of that therapy ultimately inspired the newborn screening program. So the fourth pillar of inborn errors is newborn screening. This is Robert Guthrie, one of my personal heroes. He was a very humble scientist who created newborn screening through the Guthrie bacterial inhibition assay. And this is one of the very first babies with PKU who was diagnosed using his test. One of the really ingenious things that Guthrie did was he created a test that could be run from a filter paper. He invented the dry filter paper method, which has really revolutionized and democratized newborn screening all over the world. So keeping these sort of 4 pillars in mind, let's take a look specifically at MSUD. So MSUD was discovered almost exactly 100 years after the discovery of the principles of heredity in plants and animals. It was discovered by this trio, Dr. Menkes, Hurst, and Craig. And it's interesting and instructive to go back to that original paper. This is a table from that paper. It describes 4 children. What you'll notice is, if you look from left to right, you'll notice that all of them were diagnosed around 3 to 5 days of age, and none of them survived beyond 2 weeks. They essentially all had convulsions, rigidity, irregular respirations, and then a characteristic odor in the urine, which gave the disease its name. In that paper, they really couldn't do anything to treat those children, and at the time that MSUD was discovered, it was uniformly fatal within a couple of weeks. But they actually described some of the key clinical features of the neonatal classic onset that still young doctors around the world use to make that diagnosis from this gestalt collection of symptoms and signs. One of them is this feature, epistatonus. This is something nobody ever wants to see in a baby. This is what doctors will often refer to as convulsions. It is not a convulsion, so it's not a seizure per se. It's an involuntary muscle spasm of the muscles of the back and neck. It's related to an acute deficiency of dopamine in the brain caused by high leucine levels. This can be reversed with high tyrosine dosing enterally, but it is often an alarming and early clinical sign of classical MSUD. Babies with classical MSUD develop something called Cheyne-Stokes respiration. This is a respirometer tracing that shows this irregular pattern. So that's a classic finding of early MSUD. And then, of course, the most feared complication, which is this diffuse and severe brain swelling, which in the case of the Menkes paper was the cause of death in all 4 cases. Interestingly, in the paper, they recognize that there's a volatile organic compound, meaning there's something in the urine that vaporizes and gives off a sweet smell. But actually, it was going to take another 5 years before they figured out what that was. So Dr. Menkes, in a follow-up paper, had isolated the keto acids of leucine, isoleucine, and valine as being the volatile substance that you could smell in the urine. And it was this finally that allowed them to establish the enzymatic defect. So this enzyme defect sits at a pivotal place in a much more complex set of reactions. These are the degradation pathways for the branch chain amino acids, leucine, isoleucine, and valine. Starting at the top, they all undergo a common step in which a nitrogen group is peeled off the backbone of the amino acid. Then they subsequently go through a series of multiple degradation steps and ultimately end up contributing to energy metabolism in the body in some way. And the reason I'm showing you this slide is if you look at where the MSUD block is, it's at the entry point for all of these other chemical pathways. And each one of the enzymes shown in blue is actually another inborn error of metabolism. So it turns out that the large majority of organic acid and amino acid disorders known in humans are elements of this pathway, and MSUD sits at the very top of it. So the first attempts at treatment for MSUD were not until 1961. There's a seminal paper by Denton Westall in which they had one child with MSUD, and they were going to try to apply Horst Bickel's principle. But there wasn't any kind of formula for MSUD at the time. This child was already quite symptomatic, had some growth failure, had pretty significant neurological delays, motor delays, repeated attacks of dystonia, which is another word for the epistatonus, visual inattention, so what we call cortical blindness, and a variety of other symptoms characteristic of poorly treated MSUD. Because they didn't have a formula, what they did was they took the chemical composition of some readily available elements. They looked at normal protein and said, well, if you take the amino acid composition of normal protein, milk protein, for example, about 10% of the protein weight of that protein is leucine, and about 6% is isoleucine, and about 6% is valine. They knew that the protein that was in common gelatin, so what is in your Jell-O, actually only has 2% leucine, 1% isoleucine, and 1% valine. They also were able to filter modified casein in a way to remove leucine and isoleucine, but slightly enriched for valine. So they used these variant protein sources and did a variety of experiments in this child. And of course, this is a complicated table, so I don't expect you to look at the whole thing. I highlighted sort of the important part. This is looking at blood leucine levels, if you follow across, on various diets. So on diet, the blood leucine level is 21. And some of you are thinking, 21, that's not bad. So this is 21 milligrams per deciliter. So you take that number and essentially multiply it by 100. So a level of 21 is approximately 2,100. So these are very high levels, very sick child. You can see that on the control diets is still levels in the 2000s. Notice when they gave the child a gelatin diet, it worked. The levels came down to 568, 460, 445. So quite effective, actually, for the time. But then they actually had the boldness to add pure leucine to the diet just to see what would happen. And this was a common, unfortunate practice back in those days, is doctors did experiment on patients quite a bit in ways that were sometimes harmful. It's sort of part of the legacy of trying to understand and learn about these disorders. But I want you to notice something else, which is relevant today. If you look at the isoleucine, you'll notice that it's relatively high in the starting condition, levels of approximately 800. It goes down. Then it goes up again. Look at the last column. The isoleucine, when they give free leucine supplement, the isoleucine plummets down to 50. We see this today with giving isolated isoleucine, valine, or leucine solutions. We see this seesaw phenomenon. The baby developed this severe rash, which they called flexural eczema. We now know that this is essential amino acid deficiency. This is the earliest symptom of essential amino acid deficiency. This is a baby with isoleucine deficiency. Leads first to skin problems, then anemia. Ultimately, it can stunt brain development. And this study, importantly, outlined the two horns of the bull in MSUD nutritional therapy. We need to restrict the accumulation of potentially toxic levels of leucine, but we also have to guard against essential amino acid deficiencies. And still in many parts of the world where they don't have sophisticated dietary management, this is a very common phenomenon in MSUD babies. They get very sick from these nutritional deficiencies. There's one other important lesson about this paper. They were able to make the baby better, and then they stopped treatment and the baby died. And why did they stop treatment? Who knows? Does anybody take a guess why they stopped treatment for the baby? Oldest story in the book. They ran out of money. They ran out of money. It's very expensive to make this diet for one child. let alone a whole group of children. They ran out of money, and that was ultimately the cause of death. So let's jump ahead a little bit into kind of the modern era of our understanding of MSUD. So period between 1987 and 2003 was a major period of research into the basic mechanisms of how MSUD affects brain development. And this work started with some elegant studies of how the amino acids cross from the blood into the brain. This is a latex model of the human vasculature. So this is the real human vasculature injected with latex. It just shows you that the brain has the densest vascular supply of any organ in the body. And the brain has a special lining on its blood vessels called the blood-brain barrier. The blood-brain barrier acts like a selective gate, letting certain things into the brain and pumping other things out. It's sort of like a protective surface. And one of the things that it allows in is amino acids. And in an absolutely beautiful set of experiments in living rats, Quentin Smith and colleagues in the 1980s and 1987 demonstrated convincingly that there's a group of 10 amino acids, most of which are essential, that are relatively similar in molecular weight and physical structure and share a common gate to get into the brain. This is the group, and you'll notice 3 of those are leucine, isoleucine, and valine, our 3 branched-chain amino acids. And it turns out that these amino acids only enter one at a time. It's a revolving door. And so they all compete with each other for entry into the brain. And if any one of them is severely elevated, it actually blocks out the other competitors. So this led to a key insight about one of the mechanisms of MSUD brain disease, is that leucine probably is neurotoxic not through its direct effects on the brain, but based on the fact that it restricts or starves the brain of other essential amino acids. So just like that child who had an essential amino acid deficiency that affected the skin and the blood cells, a selective amino acid deficiency can affect just one organ, the brain. And this explained an interesting phenomenon in the neuropathology of MSUD. This is a paper from 1992 showing on your left a nerve cell network from a normal human brain. So this is what the nerve cells look like when they're stained with something called a Golgi stain. That sort of creates this perfect black silhouette of all the nerve extensions. You can see the MSUD brain on your right. You'll notice there's fewer nerve cells. They have fewer branches and fewer connections. This is identical to the neuropathological appearance of protein starvation. So this is the neuropathology of essential amino acid deficiency, and we believe it's this starvation mechanism that is really how leucine affects brain development. Now, isoleucine and valine also have an effect. It turns out that leucine has by far the highest affinity for the transporter. Leucine's a very strong competitor and thereby probably exerts the largest effect on brain development. So it would be a few more years of development around this idea until another major hypothesis was developed by 2 researchers, Mark Yudkov and Itzhak Nissim, who in 1996 identified this other core mechanism by which MSUD probably harms the brain. This is a little bit complicated, so I'm just going to keep it as simple as possible. But the transaminase is the enzyme right before the MSUD enzyme. So the MSUD enzyme is called branched-chain ketoacid dehydrogenase, BCKDH. The enzyme right before it is this enzyme, and its role is to take the nitrogen group off of each amino acid and transfer it to something else. And so in the brain, this has a special role in transferring nitrogen to glutamate and GABA. Glutamate and GABA are the most abundant neurotransmitters in the human brain. So about 85% of the electrical messages that are sent in your brain in this moment are mediated by glutamate. And the nitrogen from leucine is used to make about 50% of that glutamate. So this explained one of the puzzling findings in early neurochemistry studies going back into the 1960s, which was they found that MSUD brains had very low glutamate and GABA levels when patients were in acute crisis. And we now know that that occurred because high ketoisocaproic acid levels, the keto acid, reverses this reaction. It actually drains the brain of glutamate and GABA and actually increases the internal concentration of leucine in the brain. We now have good reason to believe this is the core mechanism of acute encephalopathy and brain edema. So we really no longer think of leucine itself as the driver of the acute crisis that everybody fears. We believe this is the central mechanism that drives that. So these studies really allowed us that by around 2020, we had a really integrated view of the pathophysiology of brain disease and MSUD. And this is a complicated slide. I put it up here only to emphasize that we now have a map for thinking about how MSUD harms the brain. And this was really a powerful foundation for improving therapy. We could really think quantitatively about what's the effect of the amino acid composition of formula. What are the various ways in which acute treatment can lower the ketoisocaproic acid levels and control them quickly so that they don't cause severe brain swelling? It's important to mention that a lot of these ideas were implemented at the Clinic for Special Children. And this is Holmes Morton, who many people will know or certainly know his name. And he's, he was really a pioneer and sort of a heroic figure in the MSUD story. He and his wife Caroline, working with the Mennonite community, established the Clinic for Special Children in 1989. And one of the really important things that they showed is that you can provide high-quality MSUD care and excellent outcomes in an underserved rural setting by putting in place effective monitoring procedures, inexpensive medical services, and really good acute hospital services that were available in people's backyards. This is a book that was published by Mennonite families who had children with MSUD. It documents the history of MSUD in the Mennonites before the founding of the clinic. It's out of print. It's a very rare book. If you ever visit the Clinic for Special Children in Gordonville, PA, there's some copies of this. I would encourage you to get a copy of this. This is a sort of a landmark to Jordan's talk. This is the first time a large group of families shared their voice. They told their story, and it's very painful to read it. They're harrowing tales of people who never got an answer until their child was fully disabled, people who went through multiple children who had MSUD. But it shows what is possible by constructing good local services focused on the community. Dr. Morton and I did a lot of work in the early 2000s to create new metabolic formulas for MSUD. And these metabolic formulas were based on the principle of brain transport. So they were not only restricted in the branch chains, but we started enriching the formula with the other competitive essential amino acids. So we used these formulas to compensate for this competition mechanism, and it appeared to improve outcomes, both cognitive and growth outcomes in children. Right around that same time, we started a collaborative effort with Dr. Mazarregos and his team at University of Pittsburgh on elective liver transplants. Now, transplant is now an accepted option for MSUD. We would say that it's, families have a choice whether they want to do restricted diet or liver transplant. There's not a right or wrong choice, but most clinicians would accept that that's a legitimate choice that families have. It was not so in 2003 when we started this. It was very controversial. Most metabolic physicians were very hard set against the idea. But of course, they didn't have MSUD. So this was an interesting story because it arose serendipitously, as a lot of medical discoveries do. And it arose from a case of vitamin A-induced liver failure in a young patient with maple syrup urine disease. So this was a child who had been getting some immune booster supplements. They were very high in vitamin A. Vitamin A is poisonous to the liver at high doses, and it causes an irreversible form of liver failure. She required a liver transplant to survive, and lo and behold, after the liver transplant, all of her branched-chain amino acids normalized, stabilized. She was put onto a regular protein diet and is alive and well today with still a functioning liver transplant. It took another 5-6 years before we started seriously considering the question about whether it's reasonable to do this electively for patients with MSUD. And in 2006, we published the first case series of 10 cases. Now there's been over 140 cases performed at UPMC and more than 240 nationally. For patients, it has been a life-changing experience. Parents will tell you that it feels like this sword over their neck that has been lifted. This thing that was hanging over them like a guillotine every day, every flu, every illness. Patients will say, I just love to eat normal food. Like, I love to feel normal. Like, I want to go camping with my friends and eat a hamburger. I want to go fishing and actually get to eat the fish when I catch it. So I was really impressed with how the removal of the stigma of having MSUD was a powerful incentive for people to get transplants. We also learned that transplanted MSUD liver can save somebody else with liver disease. It's called a domino transplant. This is a MSUD patient who gave her liver to a PKU patient who wanted to have a healthy baby and was afraid of maternal PKU, and now has had a healthy baby with this MSUD liver. The transplant outcomes are excellent. They're not perfect. Transplant is a difficult procedure. It is dangerous, and there are many bad things that can happen, both in the short and long term. But the truth is we now have over 20 years experience with this, and the outcomes really are exceptional. Overall survival greater than 94%, functional cure in essentially 100% of cases, which means elimination of metabolic crises, elimination of any dietary restrictions. Also a chance that we've all become really good friends. That's been a great chance for Dr. Mazarregos and his team and our team at CSC to develop a long-standing trusted friendship and partnership. So what's next? So the new frontier for MSUD, and I'm going to close here in a moment, and I will talk about this a little bit more today, so this is not the last time we're going to talk about it, is what we call precision therapies. Now, you refer to them in shorthand as gene therapies, but I prefer to think of the broader class of precision therapies. This means identifying the root genetic or molecular cause of a disease and going to that specifically to prevent all the downstream consequences. We may address that through replacing a gene that's missing. We could address it through editing a gene that's misspelled or broken, or any myriad other ways. We may develop small molecules, genetic molecules, that can go in and bind onto the error and help mitigate it or help the error be read differently by the cellular machinery. So there's any number of ways we can imagine. The key idea is that we're trying to correct the root cause of the problem. And we now have the genetic knowledge and some of the tools that will allow us to do that. With the UMass team, we developed this precision therapy. This is called a dual gene vector. AAV9 stands for adeno-associated virus 9. What this is it's a hollow viral shell that's been genetically engineered to contain the two genes missing in the two most common forms of MSUD. MSUD type 1A and type 1B. The BCKDHA and BCKDHB gene form a catalytic complex and together account for about 80% of all MSUD cases worldwide. They also account for most of the classic or severe cases. This viral shell acts as a delivery system, like a molecular syringe. We inject it into the bloodstream. The idea is that it encounters human cells, binds onto their surface, and injects the genetic material. That genetic material should survive the life of the patient in those cells, which means this therapy is intended to be a one-time and done therapy. It constitutes a 60-minute infusion with some immune protection, prednisone, for about 30 days afterwards. If it works, life without MSUD after that. This is the hope. This vector works really well in cells that have MSUD. It rescued 2 different mouse species with severe MSUD and actually a cow, a young newborn calf with MSUD, who is now approaching her 5th birthday and is still cured of MSUD. So I'll talk a little bit more about that later. I'm going to finish up. I just want to say, I have so many colleagues too numerous to thank. I'm especially happy to thank Dr. Mazarregos, who has just been so great to work with over the years, all my colleagues at the Clinic for Special Children. But I want to especially say that this is all about the children and families who are here. These are the people I want to thank the most. I can't walk in your shoes, but we can walk alongside you. And I would say that throughout my career, you've always taught me more than I've taught you. So really thank you for your support of this mission. So.
Thank you, Dr. Strauss, for that very interesting and heartfelt presentation. Break time, go visit the vendors, come back.